Welcome to this video on the topic of exponential functions. In this video, we're going to investigate the graphical representation of an exponential function. To do this, we're going to look at two techniques. The first one being how we can plot an exponential function, and then secondly, we're going to have a look at the features of an exponential function to be able to sketch them. Now, firstly, looking at plotting them. Over here we have an exponential function. It's defined as 3 times 2 to the power of x. This representation over here is known as the algebraic representation. To be able to plot this, we first need to convert this algebraic representation into a numerical representation, as shown with a table of values. Now, the way in which we pick the table of values is I always like to look for the y-intercept, and then we simply pick a number of values either to the right and to the left of it. If we have enough values, then we can plot. Now, the second step is we need to populate our table of values. To do this, I'm simply going to sub in the value of x into our equation and compute the values of y. Looking at all the positive values for x, what we can observe is that as x is increasing in magnitude, the value of y is increasing in magnitude at an irregular rate. What we find is that as x is increasing, y is increasing at an increasing rate. Now, looking at the negative values for x. Thus, for -1, we have a y value of 3 on 2. -2, we have 3/4. And for x equals -3, we have 3 on 8 for y. And thus, what we see is that as x is decreasing, or as x is becoming more negative, the value of y is getting smaller and smaller. Now, to be able to show this in its graphical representation, what we're going to do is we're going to get this table of values and we're going to plot it on a Cartesian plane. So getting these values here, I'm going to go down and I'm going to plot them on here. First one was at 0, 3. This is our y-intercept. Always very important to show that on a graph. Next point was at 1 and 6, 2 and 12, and then finally 3 and 24. On the negative side of the y-axis, we had -1.5, so that's roughly here, -2 and 3/4, and then we finished off with -3 and 3/8, pretty much 0. Now, next thing I'm going to do is I'm not going to get a ruler for this, but rather I'm going to try and rule a line that cuts through all of these points. And thus we've converted our numerical representation over here, as well as our algebraic representation, into the graphical representation of our exponential function. Now, one of the things that you're going to notice about the representation of this graph over here is comparing it to a linear graph. First thing you see is that this is not straight, rather the line itself is curved, that being an exponential curve. Now, for this particular exponential function, on the left-hand side of the y-axis, so in the -x region, we see that the value of y is decreasing at a decreasing rate. So the distance between y, between here and say this point and this point, is getting smaller as we go from here to here, then here to here. Eventually what will happen is that as x becomes increasingly negative, the value of y will get closer and closer to 0. It's never actually going to get there, but it gets really, really close. We'll cover this concept in a later lesson. Now, on the other side of the y-axis, so in the positive x region, what we find is that as x is becoming more and more positive, the jump between y values is increasing. So from here to here, there's an increase of 3. From here to here, there's an increase of 6, and from here to here, there's an increase of 12. So the value of y is increasing at an increasing rate. Now, not all exponentials are going to look this way. Rather, they're going to look slightly different depending on the components that make up the function. Now, if we turn our attention down to here, what we can see is the exponential function. we characterize it by saying y equals a times b to the power of x. Now, all of these variables within this equation are going to affect the overall shape of the exponential function that we're graphing. Now, labeling these, we have x, which we define as our index power or exponent, depending on what name you'd like to use. We have b, this is our base. Thirdly, we have a. This is a different one, we call this a dilation factor. Then finally we have the y, which is our, we can call it our result or our subject. Now, the two components that we're going to look at that will modify the overall shape of our exponential function are the values a, or the variables a and variable b. So our dilation factor and our base. Now, the dilation factor is going to determine the location of the y-intercept. So if we look up here, what we can see is that our y-intercept is at 3. Now, moreover, if you look at the algebraic representation here, the dilation factor is also 3. Now, on top of this, the dilation factor is also going to determine whether the shape or whether the graph is above the x-axis or below the x-axis. If you have a positive a, then what's going to happen is your graph is going to look like either this or this. But if it's negative, then it's going to be mirrored about our x-axis. So you've got negative a in these instances. Now, the other factor that's going to change the overall shape of our exponential graph is the base itself. So the base can come in two flavors in general or in stage 1 general mathematics. The first flavor we're going to have is when the base is above 1, in which case we're going to get a graph that's going to resemble what we had before in our example. However, if our base is below 1 but still above 0, then what we're going to find is that the graph itself is sort of mirrored about the y-axis. That is, it starts off with large values of y, and then y decreases as x increases. So in summary, what we can see is that by modifying the values of a and b, we get graphs that look like this nature over here. Now, one thing we're always going to find is that for stage 1 general mathematics, we never have to deal with the case where b is less than 1. Now, using our expert understanding of what the dilation factor and the base do to the overall graphical representation of an exponential function, we're very easily able to sketch exponential functions. That in by, we simply observe the nature of the dilation factor as well as the base, and we simply fit the curve that matches. So if you have a dilation factor that's positive and a base that's above 1, then you're going to have a shape that looks like this. Moreover, if you had a dilation factor that is less than 1 and you have a base that is greater than 1 still, then you're going to get a shape that looks like this. So all you need to do to be able to sketch these is just memorize what these shapes look like relative to the variables a and b. So in summary, what we had a look at in this video was, we had a look at how we could go about plotting an exponential function by simply creating a table of values and then plot it on a Cartesian plane. After that, we had a look at what the variables do to affect the overall shape of an exponential function. Variables that cause difference are a and b.